Hey everyone, I'm Yeshwanth and I'm going to be presenting our paper, Uniform Approximations for Randomized Hadamard Transforms with Applications. And this is joint work with Jelani Nelson at UC Berkeley. So let me start with a little bit of motivation. So we're going to consider the standard supervised learning setup. So here you observe a series of n data points, which consists of pairs xi, yi, where xi belongs to Rd and yi is some label that you want to be able to predict. And your goal is to learn some function that maps your input space to a real number that is relevant to predicting the label y from x. So when y is discrete, so if y is 0 or 1, f of x might simply denote a score that you could then maybe convert to a probability. So this probability would tell you the probability of each class. Alternatively, when y is, let's say, a real valued number, f of x may directly predict the label itself. And now what you want to do is you want to learn a function f, which is useful for making this prediction. Okay. And the simplest possible approach, or arguably the simplest possible approach towards solving this problem, is to simply use a linear function. So here, this function is parameterized by some weight vector w, and you represent the function as simply the inner product of w with your input x. But one problem with this approach is that linear functions are simply not very expressive, and you may want to represent more complicated classes of functions. And one incredibly successful approach towards doing this is to employ a kernel method. And these methods substantially enhance the class of functions that you can express through this class of machine learning models. And the intuition is roughly as follows. So you start by rewriting the linear function. So specifically, you rewrite the weight vector that characterizes your linear function as some linear combination of your training data points. And now you can write the output of the linear function in terms of a sum over the training data points times some parameter alpha I, which denotes the weight that you give to this training data point, times the inner product of the training data point with your test point x. And the key intuition of the kernel method is to replace this inner product in the original input space RD with some kernel functions which represent an inner product in some higher dimensional space. And the key idea behind using a kernel function is that you only need to define the inner product function. And this implicitly defines the transformation to the higher dimensional space, but you don't represent that explicitly. So you could have a kernel function that you could succinctly describe like the Gaussian kernel, which in fact corresponds to an infinite dimensional Hilbert space, but you don't have to represent it explicitly. But this approach does have drawbacks. Two major drawbacks are that at test time, it is potentially possible that you need to store all of these data points because you need to compute the kernel function with respect to them. And this, in addition, also increases your computational cost towards classifying a data point. So for a typical kernel like the Gaussian kernel, this could take time ND for each test point that you want to evaluate. And the main contribution of this amazing paper by Rahimi and Recht in 2007 is that you can compute an explicit mapping phi hat such that after you transform the input points using phi hat, the inner product in this transform space corresponds roughly to the evaluation of a kernel. So for the popular Gaussian kernel, which will be the focus of this talk, the mapping is defined as follows. So you're going to generate a Gaussian matrix with roughly d over epsilon square rows and d columns. And each entry is going to be generated as an IID standard Gaussian random variable. And the transformation simply multiplies your input point x by the Gaussian matrix G, and you add a random offset between 0 and 2 pi. And once you compute this affine transformation, you're going to take the element-wise cosine of the resultant vector. And what you can show is that if you generate your randomized mapping in this way, an inner product between phi hat x and phi hat y is going to roughly correspond to the Gaussian kernel. So this solves one problem in the sense that you don't really need to store all the data points. You could simply compute like this mapping explicitly, and you could store the linear function in this higher dimensional space. But it's still somewhat expensive to evaluate for a new input point. So since this is a d over epsilon squared by d matrix, computing this linear transformation, g times x, takes time d squared over epsilon squared. So can you do something a little bit better than this? And a natural approach is to use an alternative family of randomized matrices instead. And these are going to be structured matrices that are based on a class of matrices called Hadamard matrices. And they're going to be defined recursively in the following way. The Hadamard matrix of dimension 1 is simply going to be a 1-by-1 matrix with 1 as its only entry. And then the Hadamard matrix of dimension d is going to be defined recursively in terms of the Hadamard matrix of dimension d over 2. And it's going to be defined in this block diagonal way. So in this 2-by-2 block diagonal matrix, 3 of these entries are going to be hd over 2. And the last entry is simply minus hd over 2. One thing to note is that an appropriate normalization of these Hadamard matrices turns out to be orthonormal. And the second interesting fact is that each of these entries are simply going to be, each entry of a Hadamard matrix is either plus or minus 1. And given this definition of a Hadamard matrix, we are now ready to describe our family of structured transformations. And they're going to be defined for some repetition parameter m. Now, what you're going to do is for each I in m, you're going to generate a diagonal matrix or a random diagonal matrix where the diagonal entries are generated IID from a standard Gaussian and are going to be standard Gaussian random variables. And your transformation is going to be stackings of the multiplication of the Hadamard matrices times each of the diagonal matrices that you've defined. So since you have m of these diagonal matrices, each of these matrices is going to be d by d. And when you stack m of them together, it's going to be an md by d matrix. So the size of the final embedding is going to be of size m times d. Because you have m of these matrices and each of them results in d entries in the output. And now we'll see that this family has several nice properties. Denoting this transformation matrix by m, what's nice to see is that each row of m is going to be a standard Gaussian random vector. Recall that each entry of h is either plus or minus 1. And multiplying each of them by a standard Gaussian results in a standard Gaussian random vector. So that's nice. And the second really nice property is that you can compute this transformation in time md log d. And this is because of the recursive definition of the Hadamard matrix. So computing the Hadamard matrix times a vector only takes time d log d as opposed to time d squared for a typical matrix. But there are substantial drawbacks with this definition. One such drawback is that each row of m is no longer independent. One way to see that is that the first d entries of the first column of m are all going to be the same value, simply because of this inductive construction. And now, because you've lost a little bit of the randomness in this construction, you could ask this question about how these matrices actually compare to fully random Gaussian matrices. And the main contribution of our work is that if you only care about the distribution of the output of the entries of the output of this transformation, these matrices behave very similarly to random Gaussian matrices or to fully random Gaussian matrices. So formally, we prove the following. Suppose you have some one Lipschitz function f, then the empirical distribution of the evaluations of f on the outputs of this transformation are close to its expectation with high probability, where the number of rows is roughly what it would have been if you used a fully Gaussian random matrix. And this concentration holds uniformly over all all of the inputs, all of the possible inputs to this randomized transformation. And it achieves this property while retaining the nice computational aspect that this transformation is computable in time md log d as opposed to md squared. And for a specific application of kernel approximation, we achieve comparable guarantees to those achieved in Rahimi and Recht for the fully Gaussian random transformation with the substantial order of d speed up in computation time. Okay. So how do we establish this result? And it's instructive to go over how you would establish a similar result if you had fully Gaussian random matrices. So again, we have this Gaussian random matrix G. Each entry is IID Gaussian. And we're going to denote its rows as G1 through GMD. Note that the size of the embedding is going to be M times D. In terms to match the definition for the Hadamard setting. So denoting these rows as G1 through GMD, we're going to look at a particular input X, and we're going to look at the empirical average of the evaluations of F on the entry of the output when X is given as input. And once you, so explicitly writing this out as, 1 over MD times the sum over the outputs, the evaluation of F of GI in a product with X, we see that since each of these vectors GI are independent, each term in this sum is going to be independent and sub-Gaussian because F is a one Lipschitz function. And since you only have a sum of independent and identically distributed sub-Gaussian random variables, you can compute, you can prove concentration over a gamma net with roughly d over epsilon square rows. So in this case, roughly MD rows. And you can extrapolate to the rest of the space via a simple continuity argument. But what we can see is that, or what we will see right now, is that this netting strategy fails for the Hadamard setting. And one easy way to see that is to consider the specific input vector E1, so the first standard basis vector. And now let's consider a specific submatrix in the Hadamard transform. So we consider a specific I in M. And we look at the so we look at how the output of HDI, so the ith diagonal matrix times E1 looks. And through a simple algebraic step, you'll see that the output of this transformation is simply going to be one entry of the diagonal matrix. So specifically, it's going to be the top left entry of the diagonal matrix times the all ones vector. So one thing to note from this equation is that when you only multiply by the standard basis vectors, you only interact with a single unit of randomness per submatrix. So you only get a single unit of randomness's worth of concentration per sketch when you multiply by E1. But now if you want to use this to then get concentration over a gamma net, you need D many sketches. So you need M to be approximately D, which would be simply too large. But one positive thing to take away from this type of computation is that there are other vectors for which this transformation behaves very differently. So for example, consider a much more well-spread vector. So it's going to be the scaled all ones vector. So it's scaled to be unit norm. And we're going to consider a particular scaling of the Hadamard matrix. So you're going to scale it by root D, and you're going to denote the rows of the scale Hadamard matrix as H1 through HD. Okay, and with this scaling, one thing to keep in mind is that the scaled Hadamard matrix is orthonormal. Okay, and now if you look at H times the diagonal matrix times the scaled all ones vector, the output is simply going to be the inner product of these orthonormal rows H1 through HD with the diagonal entries of the diagonal Gaussian random matrix. And now, because of the rotational symmetry and the independence properties of the Gaussian distribution, you can see that each of these entries are going to be independent. And they're going to be distributed according to a standard Gaussian random variable. And what you can, so they're going to be distributed according to a standard Gaussian random variable. So in a sense, for inputs that are well spread, you actually get d units of randomness from each sketch. Whereas for the more concentrated standard basis vector, we only got 1 unit of randomness. And one thing to take away, or one intuition to take away from these two examples, are that the concentration properties depend strongly on the sparsity of the input vector. And in our paper, we formalize this intuition, and we obtain a sparsity-dependent concentration inequality, which somehow extrapolates between these two extremes. So we show that the deviation from its expectation is bounded in some sense by the squared infinity norm of the input vector. And you can see that when the squared, when the input vector is a standard basis vector, the infinity norm is 1. So you only get a total of m units of randomness in the concentration. On the other hand, if the input vector is really well spread, so it's the scaled all once vector, then the infinity norm is 1 over root d, and you get a total of md units of randomness. So this is a sparsity dependent bound that somehow extrapolates between these two extremes. And now consider the set of well spread vectors. So vectors for whom the non-zero entries, or the scale of the non-zero entries, is comparable to its infinity norm. For these types of vectors, you'll observe that the infinity norm roughly tracks the number of non-zero entries or the support size of the vector. And because you have this type of scaling, this type of relationship between the infinity norm and the support size, you will in effect be able to do a union bound over all such well-spread vectors. Because for each such well-spread vector, you do get concentration on the scale of its support size, which roughly corresponds to the log of the covering number of these types of vectors. So you can establish these types of concentration inequalities for well-spread vectors, but that on its own is not sufficient, because there are several vectors that are neither really well spread nor are they very sparse. So for example, consider a vector that's simply the sum of the first standard basis vector plus the scaled all once vector. So in the visualization that you see here on the right-hand side, you see that it has a really large leading entry, but all the other entries of the vector are pretty well spread. And this poses a problem for the inequality that we had on the previous slide, because the infinity norm of this vector is quite large, so it's omega of 1. But there are exponentially many of these vectors in a covering of these types of vectors, because there are exponentially many vectors which are well spread over the remaining entries of the vector. So doing a union bound using the concentration inequality that we had over the previous slide is not feasible for vectors of this form. So the final step in our proof is to establish a conditional concentration inequality. So formally, it goes something like this. So suppose you have a vector u that's decomposed as a sum of two vectors, u1 and u2, who have disjoint supports. So the supports of u1 and u2 are disjoint. And consider the set of random variables which correspond to those diagonal entries of the diagonal Gaussian matrices which define our Hadamard transforms that actually interact with the non-zero elements of U. So you only consider those elements in the diagonal Gaussian matrices which belong to the support of U2. Then you can show a conditional concentration inequality that only depends on the properties of U1. So it only depends on how well spread or how concentrated U1 actually is when you condition on the variables that correspond to the entries of U2. And the way we will use this inequality is by conditioning on the concentrated segments of the vector, and we will union bound over the well-spread portions. So what this inequality tells you is that the concentration that you get for the well-spread portions depends only on the properties of the well-spread portion. So a union bound is actually feasible over these types of vectors. So for example, so how would we use this inequality for the example that we saw before, which is the sum of the first standard basis vector and the scaled all ones vector? We're going to decompose it as the sum of the well-spread component, which is a scaled all ones vector, and a really concentrated component, which is the first standard basis vector. And we're going to condition over the variables that belong to the support of U2. So that belong to the support of the first standard basis vector. And we're going to union bound over vectors that look like U1, so well-spread vectors. Okay. And now since vectors like U1 are well-spread, the union bound now becomes feasible because the infinity norm of U1 is simply 1 over root D. So you get D units of randomness for each sketch. So a union bound is actually feasible. And furthermore, since the support of U2 is small, we can also include U2 in this conditional concentration inequality. So we can simultaneously do a union bound over all possible values of U1 and U2. Okay. So how would we do this for a general vector V? What we show is that, or it's also quite simple to see, is that you can decompose a general vector V as a sum of R vectors, U1 through UR approximately, where R is not very large, it's only logarithmic in D. And the support sizes of consecutive vectors in the sum are increasing. So U2 has a larger support than U1 and so on and so forth. And within each of the subcomponents UI, they're well spread and their supports are disjoint. Okay. And because of this particular decomposition, we can now establish a conditional concentration inequality where we condition on subsums of this decomposition. So we are going to look at the concentration of the transformations of U superscript K, which is a sum of all the, which is a subsum up to the first K elements of this sequence. And we're going to condition on the support of the previous subsum. So the subsum up to K minus 1 elements in this decomposition. And now we have this conditional concentration inequality for subsums of this decomposition. But we still need to show that just because we have a conditional concentration inequality, this conditional concentration inequality, this conditional expectation is actually close to its true value. And there is a somewhat technically involved inductive argument which stitches these conditional inequalities together, or these conditional expectations together, that this is indeed equal or close to its true expected value. And that concludes the proof of our main result. And now I'm going to discuss some open questions. The first open question is whether we can show similar concentration inequalities for other stable distributions. So we showed our concentration inequality specifically for the normal, specifically for normal random variables, which is the two stable distribution. But can you establish such an inequality for one stable distribution, which is the Cauchy distribution, for instance? And one drawback is that our current proof relies strongly on the Gaussian assumption. So it's not clear how to incorporate these other more heavy tail distributions into our analysis. And in terms of applications, this result would have applications to other important kernel functions like the Laplace kernel. So our result only applies for the Gaussian kernel that we saw at the beginning of the talk, but it would be nice to see similar sort of advancements for other important kernels. And a second exciting open direction is to explore the concentration properties of such structured matrices when you optimize over them. So can you use these matrices as subcomponents in large machine learning models like neural networks, where you explicitly optimize over these weight matrices? And these matrices have been empirically observed to be useful in various machine learning domains. And it would be nice to see if we had a more concrete theory over why they work so well in these domains. With that, I'll conclude my talk. Thank you for listening, and please feel free to reach out if you have any questions.